Good afternoon. My name is Marty Golubitsky, and I'm a faculty member in the mathematics department here. I'm also associated to the Mathematical Biosciences Institute, the center that is sponsoring today's talk. And it's my pleasure to introduce today's speaker. First, however, I must apologize to those of you who came to hear Paul McEwen. A couple of weeks ago, he had some family difficulties and he had to cancel. Well, there's a small silver lining in this. This gave us the opportunity to show you how many interesting faculty members there are in the College of Arts and Sciences, which is one of the sponsors of this program. As some of you may know, several years ago, Ohio State decided to grow its research strength in several discovery theme areas. These areas include translational data analytics and infectious diseases, both of which intersect MBI interests. This program enabled us to attract today's speaker, Elisabeth Root, and she came to Ohio State last year. Professor Root's research lies at the intersection of geography and public health. She uses spatial statistics and GIS, and for those of you who don't know what that means, and I didn't, it's Geographic Information Systems, to integrate socioeconomic and environmental data into studies of disease and health. Elisabeth has active research projects in Honduras, Bangladesh, and the Philippines, as well as in the United States. And indeed, when I emailed Elisabeth to see whether she'd be willing to speak at today's Science Sundays talk, I got a response within 12 hours from the Philippines. If you could join me in welcoming Elisabeth Root, who will speak on Has Cholera Met Its Match? Geographic Science in the Fight Against a Global Killer.
Well, thank you for joining us this afternoon for this Science Sunday talk. I realized that I put the wrong date. I think it's actually this 4th, right? So I'm a day ahead of myself, so sorry about that. But today I want to tell you a story about cholera, which many of us living in developed countries don't really think is much of an issue anymore. And yet it was a massive scare to places like New York City and New Orleans and Memphis, Tennessee in the 1800s in the United States. One of the very first global diseases, really, cholera, partially because it's one of the first diseases that we watched spread from Southeast Asia to the Americas in a time when there was very little spreading between these two regions. In the telling, I hope to show you how important and powerful geography and geographic science are to the study of human health. I also hope to teach you a little bit about my subspecialty within geography, which is called Health and Medical Geography, or Spatial Epidemiology. I know some of you in the room are probably wondering, what is geography? It's not formally taught in primary and secondary schools in the United States, and it is by no means the most popular major at US universities. But, and in fact, many universities don't even have geography department, which those of us who work in geography think is quite a crime, because we are sold. Geography is an extraordinarily diverse discipline. I often refer to it as the multidisciplinary discipline because our research scientists study topics from groundwater hydrology to climate change and polar ice dynamics to globalization, indigenous rights, transportation systems, pretty much every topic you can think of. It's the study of places and how people interact with those places. And that's what binds this particular discipline together. This acknowledgement that humans interact with the environment and we change it and it changes us, and how that translates into all sorts of different sciences. So on with our story. This is John Snow, a particularly handsome young man who lived in the 1800s in London, modern-day London. He is held up actually as the very first medical geographer. In 1854, in the height of a cholera epidemic in the Broad Street neighborhood of London, he published the map you see here. It's kind of hard to see because the map was very, very detailed, but basically what he did is that he located each case of cholera in this particular region, and then he also put the water pumps on this map, the places where people, the neighbors, would get their water, their drinking water. From this, he suggested that there was enough evidence to conclude that the Broad Street pump was responsible for cholera. The story goes that he took the handle off the Broad Street pump, and the epidemic abruptly ended. Therefore, he is considered the man who discovered that cholera was transmitted by water. The Broad Street map is actually shown at the beginning of almost every single introductory epidemiology and medical geography course that I have ever sat through in my entire life. That is except actually for mine. I don't even use this map in my own teaching. While I acknowledge that Dr. Snow made a really cool map, because he did, and this is very, very exciting as a geographer to see this type of science being done so early, the type of things that we're doing in geography now would have totally blown Dr. Snow away, right? We have a new technology which was mentioned earlier called Geographic Information Systems, and this has really become one of the cornerstones of geographic science. Even 5 to 10 years ago, desktop GIS, the ability to make maps on a computer in real time in a very easy, accessible manner, really didn't exist, actually. And while GPS is integrated into every single smartphone in this room nowadays, the ability to use GPS technology to locate where you are on the globe's surface, to route yourself from a restaurant to your home and back again, that actually was largely only military, accessible to the military until about 1995, when all those satellites up in the air became accessible to the public. And so geography has moved forward in leaps and bounds in the last 10 to 15 years because of this massive advent of technology. So Snow's story is actually told in this great book called The Ghost Map, which I encourage you to read if you kind of think this stuff is interesting. And basically, the book itself is about a fundamental paradigm shift in the way that people thought about the cause of disease broadly, but cholera specifically. The author of this book discusses the conflict between Snow, John Snow, a doctor, and actually he was an anesthesiologist, if you want to know what he actually did, and something called the miasmists, which is another group of medical doctors who thought about disease in a different way than Dr. Snow did. And Snow really overcame bad data, bad inference, and incorrect conclusions with really good science. And that's what I want to tell you about today, is his good science. The historical view of disease was that it's spontaneously generated instead of being created by microorganisms, as we know it does, right? Cholera was believed to be transmitted by air, and that's what the word miasma means. It basically means bad air. And so that's how people thought that cholera was transmitted. And in London, in particular around the Thames River, there was a tremendous amount of deadly miasmata, or bad air, that came off of the banks of the Thames River. And eventually, of course, this sort of bled into the Broad Street neighborhood area where that pump was located. Disease was the product of environmental factors: contaminated water, foul air, and poor hygienic conditions. Infection was not passed by individuals. This is the dominant thinking during this time period. The wide acceptance of the miasma theory of health, actually during the cholera outbreak, really overshadowed the partially correct theory that John Snow brought forth in the middle of this epidemic, that cholera was spread through water. It was so entrenched in medical science that people just could not wrap their brain around the idea that cholera came from anything other than bad air. So John Snow actually believed that these little things, he called them animalcules, that lived in water, because you could see them in the telescope or the microscopes of the day. You could see little things moving around in the water. And mostly these are sort of phytoplankton and things like that. But he believed these animalcules in the water explained outbreaks of cholera. And this was in opposition to everything that medical science was built on at the time. So the germ theory of disease, of course, proposes that microorganisms are the cause of disease. This is, of course, what we know and love now. Although highly controversial at the time when Dr. Snow was here, it's of course now the cornerstone of modern medical science, leading to really important discoveries like hand washing, antibiotics, vaccines, everything that we do in science and medical science today. Before germ theory, though, those in the medical community practiced a much more holistic medicine, and they sought to make sense of illness in a way by contextualizing a person's environment and their lifestyle, and trying to figure out what that person was doing differently than everybody else who wasn't sick, right? This is the world that John Snow operated in. People in those times just did not find it easy to accept the idea that there was something they couldn't see and touch and smell responsible for disease. It was basically scary, right? It's scary to think that there are things out there in your environment that you don't have control over that are causing disease. I'm not a medical historian, although I find it very fascinating, obviously, in telling you this story, but I do know that there were, of course, many people who contributed to our understanding of germ theory, of not just John Snow, who actually discovered what the organism was that was causing certain types of disease. But John Snow's work was really, really important in starting this paradigm shift in medicine. So back to the study that Snow did. This is actually a map that he created of water systems and the geographic regions that they served in London. That's the Thames River on the top that runs through this area. And the different colors denote different water systems, different companies that provided drinking water to different areas of the city. He used very modern, actually, public health tools to examine his theory that cholera and water were related. Yes, he created a map. He actually created a series of maps in his publication. But he did a bunch of things that utilized geography. He collected data, and he assigned it to a location. We call this georeferencing today in my field. He calculated statistics to compare groups of people who lived in one region of the city versus another area of the city, who were exposed to different water sources. Here we see this historic map. It's actually on the mode of communication of cholera was what he published a book in 1854. And so it's elegant because what he did was he just took the different regions, and this is the table that accompanied it. So we have, this is one water company, this is another, this is another. They all had pumps that drew from the River Thames. This actually drew further upstream, downstream, and they're at the very mouth of the Thames. So as you go down here, you get further down the Thames River. And this is actually on the far side of London, where the river flows through it. And what he immediately noticed was the cholera rate was much lower here than it was here, meaning that if you drew your water from far downstream, you were much more likely to get sick. This is an elegantly simple example of how place matters to health, just where you're getting your water from. At a smaller scale, Snow actually developed a survey. He talked to people in the Broad Street neighborhood. He talked about their sanitation, their water collection habits, and their consumption habits. He contextualized this outbreak that occurred in the Broad Street area in an attempt to understand this geographic pattern that he believed he saw. Essentially what he did is he tied geographic data, the location of people in their homes, to social and demographic data. And that's what explains the epidemic, okay? So what this map is actually a recreation of that map you saw on the very first slide, where some geographer, with the modern day tools that we have of geographic information systems, put down the map and then made these dots, these red dots. A larger dot means that there's more cholera in that particular region. A smaller dot means there's less. And then the yellow are pumps that are around there, with the big yellow star in the middle being the Broad Street pump, the one that was contaminated. Honestly, John Snow's work might have totally been ignored if it hadn't been between a competition between him and a man called Henry Whitehead, who is a minister of the day and actually went around to a lot of these houses and talked to his flock to see what they thought was going on in this region and how they were relating to the water and whatnot. Between the two of them, they published a couple of seminal articles in the Royal Society of Medicine, which explained a lot of what was going on. There were criticisms of Snow and Whitehead's work because there were large areas where people didn't get sick. And if it was really about the Broad Street pump, people in those places should have gotten sick in the same way that everybody else in the neighborhood did. But when they did this ethnographic survey research, they figured out why there were anomalies. And these anomalies ultimately helped them understand what was going on. So as an example, I've highlighted this brewery right here, that building, big building. Lots of people should have gotten sick there. But they didn't have any deaths. And the reason behind that is they had a private well for one because they needed a lot of water to make beer. So they had their own well. And the workers got beer for free when they worked there. So why would they drink water when they could drink free beer, right? So they didn't have any deaths, but there was a reason for it, right? And the other one is up at the top, there's a workhouse. A workhouse was where young men, traditionally unmarried men, would go and live while they were working in the city. It was sort of where migrants into the city came to. And they actually also had their private well, and there were only 5 deaths, despite the fact that there are 100 people that lived there, right? So by contextualizing and tying in social and demographic information, we can understand much more readily what's going on at a small scale, small geographic scale, when it comes to outbreaks like this cholera outbreak, right? This is what health and medical geography is about. In fact, this is what geography is about. But in my field, we do this all the time, and this is where the science is at. The science is at harnessing the power of maps and GIS, and I'll talk about remote sensing in a little bit too, which is another technique we use, but marrying it with our understanding of how humans interact with place through surveys, through demographic research, and putting it all together to create a holistic interpretation of health. I find it very exciting, obviously. So let's fast forward for a bit. Dr. Snow and what he did was truly fundamentally important for our understanding of cholera, right? It totally changed the way people related to this major disease that was frightening, that was scary to people in the 1800s. But unfortunately, there's still a significant amount of work to be done because cholera remains a threat to global public health, especially in low-income countries where there's a lack of public health infrastructure to provide clean water and sanitation to people who need it. And also in areas where disease surveillance is very poor, where we don't actually track disease particularly well, it allows outbreaks to become much worse than they need to be if we could surveil the population and understand what was going in a timely manner. So this is actually published by the WHO in 2012, just a quote from them about how cholera is still a global health problem, and in particular, it's a good indicator of development because it tells us how well a population or a country can provide good sanitary practices for their population. And many developing countries lack that. So this is a little timeline I put together about cholera, and I'm going to talk to you about it because there's a couple of important key events that have happened in the last little bit. The first recorded instance of cholera was in 1563. That's a long time ago, and it was reported in an Indian medical report. The disease actually was confined to the Ganges River Delta until about the early 1800s. In health science, we say that cholera is actually endemic in the Ganges Delta region of India, and that means that it sort of always exists there in a very low level in the population. So you'll see a cholera case pop up here and there, but nothing sort of that blows out of control. So it's considered to be endemic. In the 1800s, our world changed dramatically. With the opening of the Americas and the technological advances that came with the Industrial Revolution, people began to move in a way that's unprecedented in human history. New trade routes opened up. Families migrated to other countries. People began to leave their rural farms in search of opportunities in these new urban centers that were opening up. In the 1800s, this was a big deal. This has never really been seen before in human history. This created the opportunity that cholera needed to become a worldwide epidemic. This is really the beginning of it. And we call this in health sciences a pandemic. A pandemic is when the disease kind of gets out of control at a global scale, right? We have an endemic, we have epidemic, which means that we have a peak, we have more cases than we would expect to see, and then we have pandemics. And that's what we began to see in the 1800s, is pandemics of cholera. So the story of cholera, and actually its worldwide distribution, is really one of economic development, migration, and change in the way that humans related to the earth. Pretty amazing stuff. So you can see that John Snow's epidemic happened sort of in the middle of the third epidemic. We have the first 5 epidemics that occur in the 1800s, and these pretty much go global. And John Snow's kind of right in the middle of it, in the middle of the third one. We discover in the mid-1800s what actually causes cholera, Vibrio cholera. Koch actually discovers it and sees it in a microscope and actually cultures it for the first time. Then we have the 6th pandemic, which strikes in about 1900. What's very interesting about the 6th pandemic is it never made it to the Americas. And in fact, until the Peruvian outbreak in 1991, we actually hadn't had cholera in the Americas for almost a century, which is pretty amazing. So the 6th pandemic strikes, and what happens is that stimulates a bunch of infrastructure development, because we know now what causes cholera to occur. And so you see cities like London and Paris and Rome and even New York City and Louisiana down in New Orleans invest in infrastructure so that the cholera epidemic can basically be suppressed. It's a pretty amazing time. And then what happens is we have this 40-year period that's called the pandemic-free period. Cholera basically disappears around the world except for this small area where it's endemic in the Ganges River Delta. And a lot of that is attributed to the fact that people just really finally understood why people were getting cholera, and we fixed the problem. Then what happens is Mother Nature takes her course, and we see the evolution of an entirely new biotype of cholera called L. tor. And L. tor is interesting because the classical biotype that actually had existed prior to that offered no protection whatsoever to L. tor. So usually when you get a form of cholera, you get immunity to cholera for a while. You can't get it. Not indefinitely. It's not like the chicken pox where you get it once and you can never get it again. You can get cholera again eventually, but it takes your body a while to forget what cholera looked like. But L. tor, there was no cross protection. And so we have this massive 7th pandemic that hits the world of this L. tor biotype. And in fact, it gets to the Americas in 1991. It's actually evolved an ever so little bit. So the type of L. tor we see in Peru isn't quite the same as what we saw in Africa and Asia. And then we have another outbreak of 0139 serotype, which is actually a heavily evolved form of cholera. And again, L. tor and classical biotype offer no protection whatsoever again. So now we have this totally new biotype on the scene. And 0139 and L. tor and classical all coexist in different ecological niches around the world now. So we have all 3 of these different things occurring. What this tells you is that we're still not clear of cholera, right? And in fact, if you remember, there was the massive Haitian outbreak that occurred after the earthquake there in 2010, ostensibly brought by UN workers who were trying their best to help people during the earthquake, but they transplanted a type of L. tor cholera to Haiti, and Haiti had been cholera-free for 100 years. So it's still a major global health concern. This is actually an interesting geographic study of the 7th pandemic. So this is the pandemic we're in right now. You can see that it evolved out of its sort of homeland hearth of the Ganges River Delta. And by 1960, had spread to most of Southeast Asia. You couldn't find a real cholera-free country there. The ones that are kind of gray are usually the ones that don't have data because they don't have surveillance systems set up. By the 1970s, you can see Africa was extraordinarily hard hit. Africa is certainly one of the regions of the world that is least developed in terms of public health infrastructure and disease surveillance. So things often hit them harder than most, no matter what. And then by 1990, we see that this particular pandemic has spread to the Americas. This is a pandemic. If I showed you maps of HIV, it would look something like this, right? You only have a pandemic when the geography explodes like this. So what I would say is notice about this map that all of the really heavily hit countries are less developed, low-income countries. So places like America, Australia, Canada, and Europe are pretty much protected. Most of the little lighter colors you'll see here are what we call imports. So somebody went off to Bangladesh, like myself, where I work, ate something they probably shouldn't have eaten, and come back and are diagnosed with cholera when they get home. But it's not endemic in those areas. It's not being circulated in these areas. So this puts us back to the quote that I just told you about the WHO. We have countries that this is still a massive public health crisis. This is actually the timeline of the 7th pandemic. You can see here 1991, this is when it gets imported into the Americas, and that's what that pink color is. Those are American cases, America's cases. And so you can see 2 distinct epidemic waves. So this is the epidemic that hit the Americas in the 90s. This, any guess what this epidemic is right here? Mostly? It's Haiti. So all of these cases occurred in Haiti. That's frightening. That is a country that did not need a cholera epidemic to occur. Cholera is actually quite a complex disease. So this is kind of where we get to the science, fast forwarding to the future. It has ties in the environment. It has ties to climate and the living conditions of the human population. But let's first talk about the climate environment piece. Vibrio cholera lives in small copepods. And this is a picture of a copepod that the cholera bacteria actually lives in. And these copepods live in brackish aquatic environments in tropical regions around the world. In fact, we believe that the copepods that are most suited to harboring the cholera bacteria actually originate in the Bay of Bengal, right? So that particular tropical climate. These copepods feed off plankton and algae along those coastal environments, and they're really sensitive to changes in the aquatic environment. Cholera exhibits actually a seasonal cycle, so you can see it peak and then die off during the colder months. This is due, of course, to regular seasonal changes. Sunlight, temperature, precipitation, these all sort of affect the growth of algae in these aquatic environments, which in turn, of course, affect the copepod populations. But there's also a much larger climate dynamic issue that's going on here. And this is what has scientists really concerned about human health. There are very few diseases that are super sensitive to climatic changes. Cholera is one of them, malaria, dengue, some of the mosquito-borne viruses. But cholera, because of this commensal relationship with the copepods, is really sensitive to climatic changes. When sea surface temperatures increase, this actually increases ocean chlorophyll concentrations. And this ocean chlorophyll increase actually increases algal blooms, which increases the amount of food available for these copepods. Copepods flourish when sea surface temperatures rise, providing a more extensive environment for cholera as well. Sea surface temperatures are related to overall global climate change, as well as El Niños. So we have some fluctuations that are due to El Niño and La Niña. Climate scientists agree that the Earth's oceans are getting warmer and that El Niños are becoming more intense as time goes on. We've seen one of the most intense El Niños ever in this last year. This sets the environmental stage for cholera outbreaks and cholera epidemics. Much of what we know, actually, about the impacts of climate and climate change on cholera comes from geographic science. Geographers have been involved in the very beginning in how do we understand the planet and the climate and how it relates to human health. This is actually a schematic, which explains a little bit about what a geographic information system was. Mentioned a couple of times so far. But basically what a GIS is it's a collection of hardware and software and the user, me, right, that sits on a computer environment. I use it on my desktop computer, which I'm doing this presentation on. And basically what it is, it's a way of integrating all of the information we have about the Earth's surface into one platform. Think about Google Maps, right? Every time you go to Google Maps, there's streets, right? You can click on the satellite imagery and it can show you the top-down of all of the different buildings that are in a particular area. But it also has information on the location of like businesses. So if you say restaurants near me, enter, it will show you the location of restaurants and even some information on them. And then if you asked it to, it would route you to that location, should you choose to do so. What Google Maps has is street data, which is the top up here. It has buildings data and all that sort of stuff. And then what we can also integrate in is what I call here land use data, but basically information about the Earth's surface. What sorts of plants grow where? What does the sea surface temperature look like? The maps you see on the nightly news that show you the cloud cover and the temperature, those are actually layers in a geographic information system that you can use to understand what's going on the Earth's surface. The GIS environment, Geographic Information Systems, allows us to integrate all of these different pieces of information into one platform so that we can see the Earth as a representation like this. This allows us, as health researchers, to integrate that climate data, that sea surface temperature data, information on ocean chlorophyll concentration. It allows us to integrate streets and people and demographics and where people are living and where they're migrating. All of this information in one platform. This is revolutionary in our understanding the way people interact with their globe. Add on top of that, even more information. That's why I was hired as a translational data analytics person. I get really excited about all this information that's out there. So we have another technology that we use, not just in geographic science, but also in atmospheric sciences and climate sciences, called remote sensing technology. There are, at any given moment, hundreds of satellites revolving around your heads up in the sky right now. There are so many satellites up there, it's beginning to get a little like space junk. And this is actually a schematic from NASA that has a couple of the big satellites that are up there right now, Calypso, Aqua, Oko-2. Each of these satellites has different instrumentation on it. And in fact, the Aqua satellite, which is pretty new, has about 5 different sensors. What remotely sensed data does is the satellite emits some sort of a light wave or radio wave or infrared wave down to the planet. It bounces off the planet, right, and it's received back by that satellite. And then what's done with that is that it's processed as big data, processed in a remote sensing or GIS environment, and information is extracted from that on the features and objects on the Earth's land surface or in the oceans or the atmosphere. So different sensors target different things. We have this great one called MODIS, which actually lets you look at the features of the land. One of the ones that I work is called CWIFIS. They have great names, all of them. CWIFIS only is there for monitoring ocean chlorophyll concentration. The JSON-1 sensor is there for doing sea surface height. All of these sensors target different things. So we have a whole bunch more data that we can add in. What remote sensing does is it actually reduces manual field work. It is nearly impossible for us to collect data on the deep sea ocean. You'd have to go out, you'd have to collect it, right? And these are really intractable places to reach. It's very hard to get to the deep sea. So we can retrieve information for places that are hard to reach. We can collect data, a lot of data, in a very short amount of time. And then we can actually integrate all of the information to understand what's going on the Earth's surface in a way that we have never been able to do in human history until we started floating satellites up in space. So over here, these are actually the 3 sensors that I use for most of my work on cholera. They're called CWIFIS, AVER, and JSON. And they extract data on sea surface temperatures, sea surface height, and chlorophyll, ocean chlorophyll concentrations. And these are fundamentally important for our understanding of copepods and aquatic environments and how cholera might be related to these different things. So actually, this is just some of the data that we can collect. This is what happens when you capture data over time from a remotely sensed source. We can make composites like this, and we can use them, of course, to monitor ocean and atmospheric changes over time. This is sea surface temperature anomalies, so deviations from sort of the average temperature of the seas in 1997 and 2015. And what you can notice, I think, is that in 2015, our oceans were quite a bit warmer than they were in 1997. So it's very interesting. And the big thing I think that remote sensing allows us to do that we haven't been able to do in the past is to capture all of this over time. This temporal piece is dramatically important when you're talking about a disease that has a seasonal cycle, that has patterns that change over time. So adding this temporal component is dramatically important in understanding cholera. So here's some of the data that was used to initially understand how cholera was related to our oceans. This is a publication that was pretty groundbreaking in 2000, tying cholera to different climactic or ocean type events. On the left, you can see sea surface temperatures for 1 year on the top. These are snapshots for different months in 1993. And down below is actually the type of timeline we can abstract. This is 1989 through 1995, and we can extract a timeline of sea surface temperatures. And you can see that there's, of course, seasonal cycling, right? Things get warmer, things get cooler in the winter, warmer, cooler. But you can also see that there's always this little dip. This is the monsoon season. So you have this initial warming. You have a lot more movement in the ocean water during the monsoon season, and then the monsoon season ends, and then winter comes. So you see these really interesting patterns in the Bay of Bengal. Over here, we have sea surface height. And these are monthly anomalies, meaning sort of deviations from the normal. And you can also just build a timeline of this over time, as well as creating these snapshots by month. So this has been a fundamentally important piece of information, which even I use in much of my stuff. This is actually a picture of ocean chlorophyll concentrations. Sea Withis, where this comes from, is one of the newer sensors that was put up. It's not so new anymore, but it takes a while for the data to get captured and to get enough of a timeline for the data to be useful. So really only in 2000 were we able to use this data, the ocean chlorophyll concentration data. But here's a picture again of the Bay of Bengal. You can see the red coloring right along the coastline. That's where you have higher concentrations of ocean chlorophyll. That's where the copepods like to live. And then you have this timeline down below of all the different things that I just talked about. The sea surface temperature data actually shows this sort of consistent pattern over time, which I showed you. And in 1992, 94, and 95, cholera outbreaks actually also show this sort of statistically significant association with this cycling. So when sea surface temperature rises, that's the dashed line in this particular chart, so does the incidence of cholera cases. That's the red line. So the relationship, of course, was expected because warmer sea surface temperatures means increased plankton and algae growth, which is where the copepods like to live, right? So we see this cycling. You can see this one. There's a peak, and the cholera peaks along with it, right? And that's what we expected to see. But there's also kind of a strange anomaly that occurs in 1993, which is this blue area, where you see that you have really high sea surface temperatures, but there's almost no cholera whatsoever. So what's going on here? This is where sea surface height comes into consideration. So if you'll notice, sea surface height, which is this little dotted line right here, was really low this year for some reason. Kind of a strange anomaly in what was going on in sea surface height. And what we learned was that when sea surface height is higher, it inundates the coastal areas, right? So it pushes water up into the Ganges River Delta. And that means that it creeps inland. When it creeps inland, it brings the copepods with it, and it brings cholera with it. So what's happening in this year is even though sea surface temperatures were high, the water wasn't inundating the lowlands of Bangladesh, and therefore there was no cholera because people were not interacting with the copepods that cause cholera. So sea surface height has as much of an importance as sea surface temperature when we try to understand these dynamics. But here's where I get stuck. So there was a tremendous amount of research done on this, partially because of the availability of all this remotely sensed data that made geographers and atmospheric sciences and health sciences really excited, right? But we know that cholera is deeply rooted in socioeconomic situations, development, and global health, right? So I always ask, where's the human component? These are some pictures of mine from my research site in Bangladesh, which we're going to talk about for the rest of this talk. This is a woman cooking by her fire outside. This is actually the Meghna River, which is the river that runs through my study area. You'll see it in a second. And basically, it's a very watery aquatic environment. And the only time it dries up a little bit is right before the monsoon season starts. Then you start to seeing a drying of the land. This is how a geographer sees cholera. So that first schematic I showed you was developed by a bunch of environmental health scientists and climatologists. This is how my colleagues and I always map out cholera. And it looks really complex. But all it's really saying, this is actually called a disease ecology triangle, cholera is right there in the middle, is that cholera is actually driven by habitat environment, which we've just talked about, but it's also related to behaviors and populations. Children get cholera more than just about anybody else, partially because we all know that children like to touch things that they probably shouldn't touch, and they crawl around on the floor and put things in their mouth that they shouldn't put in their mouth, which makes them at higher risk for cholera. So things like age structure of a population, their nutritional status, and whether they're well hydrated. These all affect immunological reasons that somebody might get cholera. This is the part that I think is really important, because behavior modifies the way we interact with the environment. If you know that you're not supposed to drink water out of the pond that's next to you, you're not going to do it, and your risk of cholera is going to be much lower. So in order to understand how people interact with the habitat, we need to understand their behaviors and all of the things that go along with that. One of the things that most affects behavior is socioeconomic status. When you are of lower socioeconomic status, especially in developing countries, the options you have for healthcare, for staying healthy, for nutrition, all of these things are very different. Your choices and your behaviors are sort of capped by what you're capable of doing in a lower socioeconomic household. So that's where a lot of my research begins. So when I started doing research on cholera, I was very disturbed by the fact that we had not added in this human component. And so I really started searching for the role that socioeconomic status plays in epidemics when they hit. And then as I went along in my career, I then back-ended that back into the climate piece and brought it all together for this sort of holistic look. So I'm going to lead you a little bit through sort of how I went through this in my own research. So what is the effect of household socioeconomic status on the initial number of cholera cases at the beginning of an epidemic? And how does this then, how do wealthy households recover from an epidemic over time? So as I told you, there was a new biotype, 0139, and it actually hit the area that I've been studying for a really long time very hard in 1992. And so we could observe what was going on. This is my study area. It's called Matlab, Bangladesh. If you know the statistical program, it is not related in any way to a desktop statistical program. But this is Bangladesh, right? This is Matlab right here. This is Bangladesh as a whole. Matlab's right here. This is about 50 kilometers from Dhaka. It takes about 4 hours to drive that 50 kilometers because of roads and traffic and whatnot. It's actually the field site for an international organization called ICDDRB. They've been studying diarrheal diseases for a very long time. And they set up something called a demographic surveillance system in 1966. They basically do a full census on the population living in this area every single year, which means we know everything you could want to know about births, deaths, migration, health events, you name it, we know about it with this population. They also started a cholera database in the 1980s because they were one of the very first field sites for an oral cholera vaccine trial that was tried out to see if this was an efficacious vaccine for people. The population actually resides in something called baris. These are these household clusters, and they're sort of raised pieces of land where they can have anywhere between like 5 and 20 houses sort of clustered on this raised piece of land. And then there's usually rice paddy all around these raised areas, and it protects them from the monsoonal rains being up higher. In 1995, we actually built an entire GIS of this region. We know every water body that flows through it. This is actually the Meghna here, and the Donagoda flows right here. These little teeny black dots that are kind of hard to see are the location of every single bari, all 7,000 of them in this particular study area. So what we did was I took this Matlab Health and Demographic Surveillance System and the Matlab GIS that we built. There was this cholera case file, and we can locate every single incidence of cholera. And then I had to figure out some way of measuring household socioeconomic status. You'd think this was easy. We do it all the time in the United States. But actually in developing countries, measuring SES is really, really challenging because most people don't have a formal income, or at least not everybody in a household has a formal income. Many of the households are engaged in subsistence agriculture, where they grow stuff on their farms that they use to feed their families, and they're also heavily involved in barter and trade for those goods. So you have to get at it a different way. One of the most common ways to use assets. This looks like kind of a silly list of assets, but let me tell you, there are many people in my study area that do not have a bed or a quilt. So this is an asset that they can purchase and consume with the income or whatever that they actually have. Housing quality is also an indicator of SES. People build nicer houses when they have the money to do so. And they actually invest in sanitation facilities like a latrine, right, or piped water when they have money as well. And the last thing that is really important in many developing countries is education. If you are of higher SES, you educate your family. It is seen as a way of improving your family's lot in life. So we can put all of these things together and create what's called an indicator of SES that we can include in lots of different ways. So here you go. Here is the 0139 epidemic in Matlab. It hit in 1993. It actually evolved in 92 and got to Bangladesh in 93. Prior to that, you can see classical and L-Tor, the two biotypes that exist in the area. The 0139 epidemic hit. It's responsible for about 2/3 of all of the cholera cases that occurs during this time. And then it sort of slowly dies out, and it comes back to what we call pre-epidemic or endemic levels by 2007. So what I was interested in is from this peak onwards, how does socioeconomic status play into these dynamics? And actually, this is what we find. It looks like a really simple graph, and in some ways it is. We have 3 lines. We have low socioeconomic status households here. We have ones that are sort of the median or the mean for the area. And then we have these high SES households, the wealthy households in our group set. And what you notice is that in 1993, the poorer or the low SES households were much harder hit by the epidemic. So these low SES households had a much higher rate of cholera, and they were much more likely to have cholera at all. If some of these wealthier Baris didn't get any cholera whatsoever. And then as time goes on and the epidemic subsides, you see that these are sort of both coming down to pre-epidemic levels. High SES households still have worse cholera outbreaks during this time period. And actually, you'll see wealthy households, cholera rates go almost to 0. So something about it is protective. But the rate of decline is about the same. So wealth doesn't make it go away faster, basically. And this is very interesting to us because basically what it tells us is that SES actually plays a really strong role in epidemics, right? So if you're poor, you're much more likely to be hard hit. And what this tells us is that some aspect of wealth is really important. We actually tried sanitation in here to see how that worked, and it wasn't even as important, actually, as purely raw socioeconomic status. We suggest, of course, that maybe poverty alleviation programs would help. Most policymakers really don't like talking about that because it's hard to do. Like, what does poverty alleviation even mean? But definitely improving the wealth of the community would dramatically decrease cholera in these regions. So here's another kind of interesting thing. This is where I started to get into environment. So I started out really only being interested in social science, and I sort of crept more and more towards environmental health as my career went on. So one of the things we wanted to look at is to figure out whether or not social interactions and the sharing of environments affect the risk for cholera. So as I told you, there is these Baris, right, that people live in. And most Baris actually share a pond. And I'll show you a picture of this, a pond with another Bari, another family group. So if they share these environmental resources, what is the shared risk of cholera? This becomes very important when you're trying to do public health campaigns. So basically, do people who share water sources have an increased risk of cholera? And we go back to the Matlab Health and Socioeconomic data set, the cholera case file. And this time, we bring in something called Quickbird satellite images. Quickbird satellite is the most high-resolution picture of the Earth's surface that we can possibly get. It is so high resolution that it actually accurately tells you something within a 3 meter by 3 meter pixel on the Earth's surface. It's that good. This is what it actually looks like. Remotely sensed imagery has many spectral bands that you can pull out of data, and it allows you to process it in different ways. This is the infrared band over here, so it's using the infrared energy to create these images. And this is sort of part of my study region. This is actually a pond right here. You can see it, the big dark pond. And then here are 2 Baris that are sharing this pond. They're actually located on either side of the pond. This is actually some processing that we did. As I said, you can process and extract information from remotely sensed images. And this is what's called a tassel cap transformation. I've never really figured out why it's been called that, but what it does is it highlights water in this pinky yellow-orange color. And it allows you to really see what the water looks like. Here's an example down here. This is a canal that's been cut for irrigation. And you can see it's yellow and pink. And then I hired a fantastic undergraduate research assistant who went through and digitized the ponds for me, which is what these blue things become. That means that I can tie Baris to ponds, and I can tie multiple Baris to a shared water resource, which is all information that I could extract using this GIS, okay? Super powerful tool for looking at environmental ties. I know this is not usually, people aren't very interested in tables, and all I want to show you is this. There's actually a lot of things that put people at risk for cholera. Your age, your gender. Religion is actually very important in this area, Hindu or non-Hindu. Distance to water bodies. All of these things are important for predicting cholera. But what's really interesting is that if a family did not share a water source with anyone else, if this is below 1, it means they have less risk. So they had significantly less risk of cholera if they had their absolute own water source and didn't share it with anybody else. This is what we know. It's consistent with the mode of transmission, but it also offers another avenue for how we could try to combat cholera in these regions. So let's tie it all together. Local population and regional environmental drivers. This is where I really started to understand that the climatic factors and the human component interact. And can we see different patterns going on when we look at both socioeconomics and all of this rich, remotely sensed climate data? So basically, we're going to look at sea surface temperature, sea surface height, and ocean chlorophyll concentration, and simultaneously take a look at socioeconomic status and look at the relative importance of all these different things. Right, back to Matlab, here it is. But now we have this monthly environmental data. So those two are the same. This changes. Sea surface temperature, sea surface height, and ocean chlorophyll concentration. The Matlab study region is here, and the satellite area is right about here. And that's just the way the satellite imagery works. It looks like it's a long way away, but the really interesting thing is that even temperatures and heights matter that far away from the study area, which is pretty impressive. So this is the monthly distribution of cholera cases. Cholera actually has 2 peaks in Matlab. It has a pre-monsoon peak and a post-monsoon peak. These are related to different dynamics. Just before the monsoon season, this pre-monsoon period, water starts to concentrate. And what that does is it concentrates the cholera bacteria into the few water bodies that are left that people also need to use because of the few water bodies left. And so you see an outbreak during this period. And then you see it decrease during the monsoon season, which is roughly mid-June to September. That's because there's so much water falling that it's flushing the hydrological system out. And the cholera basically gets flushed out into the ocean, and people aren't as exposed to it. At the end of the monsoon, there's a ton of water around. It's really, really wet. But it's no longer flowing through the hydrological system. And so you have more water that people are interacting with, which gives us our second cholera peak during the time period. We use this data. This is the sea surface height and the ocean chlorophyll concentrations, and created timelines like this, which we could match up with our monthly cholera data and the socioeconomic data that we pulled out of that demographic surveillance system. And this is what we found. Actually really interesting. We ended up breaking down the epidemics into the pre-monsoon and the post-monsoon season because we had a hunch that they were being caused by different things. And it turns out we were right. In the pre-monsoon season, what you see is that sea surface height and ocean chlorophyll concentration is actually quite important for cholera dynamics. So it's really, the epidemic during this time period is being driven by climatic factors. But in the post-monsoon season, it's almost entirely being driven by socioeconomic status. So we have totally different dynamics at different times of the year. And this was done, we did some fancy schmancy statistical modeling, and it holds true for whatever section of the year, or whatever section of time you look at. So it's not one set of data that ended up being this way, but we actually looked at it over time, and the relationship hold this pre and post-monsoon season thing. So basically what we found is that there are socioeconomic drivers that are modifying the impact of the environment and making either the epidemic worse or better during different seasons. And again, these local level poverty alleviation programs are probably the most effective way of combating a lot of the dynamics that you're seeing in these particular regions of the world. So where does that take us? Where the state of the science is right now is that people, we feel like we have a good handle on what's causing cholera in terms of both population and environment factors. And what the world is really hoping to do is move from this sort of surveillance and response or reactiveness to a cholera epidemic toward prediction, warning, and prevention. And essentially the WHO is creating a working group, or has started to create a working group, that is looking into creating a cholera early warning system. And actually, it looks something like this. There was a meeting in 2013 that I actually went to where the WHO called together all of the experts, quote unquote, in the field of cholera, from environmental scientists to social sciences. Geography was really well represented. And this is what we walked away from. We walked away saying, our early warning system needs to include climate data. We know there's a relationship. It needs to include information on where disease is occurring, right? We need to be able to monitor it. We need a surveillance of cholera that's occurring. We actually need to understand how the cholera bacteria is evolving over time, because that's when you see these new epidemics, is when the cholera evolves and we have a new biotype or a new serotype. And then, I was very proud, SES made its little rise in here. So there's an acknowledgement that demographic and migration data and socioeconomic status need to be part of any sort of modeling and prediction effort. All of this feeds into some sort of massive predictive model. This predictive model will integrate all of the data that you have down here, and it will basically come up with maps that show where the vulnerable parts of the world is. What this allows us to do then is tweak things like, we have this model, we tweak the climatic conditions and say, what happens if there's an El Nino and sea surface temperatures and sea surface heights do this? Where do we expect to see the next major outbreak occur, right? And it will display it in our GIS on our map so that we can say, this is an early warning for this area. They need to be on the look for cholera, and they need to start doing something now rather than waiting for this epidemic or pandemic to occur. And this builds our early warning system, where we can identify where things are going to happen before they actually happen. And this is what scientists like myself are working on right now. How do we harness all of this data, because there's so much data in the world, and it's really big, and build something that could potentially save lives going forward? And that is what we hope to do. And that's all I have. Thank you for coming.
Thanks a lot. I particularly want to thank Elisabeth for being willing to stand in on short notice and produce a delightful talk. We have time for questions. I want to remind people that there's a reception upstairs on the second floor after we're finished here, or those of you who want to get an early stab at the chocolate up there, you can do that right away.
Ooh, chocolate.
In any case, if there are any questions.
Yeah. Mm-hmm. Right. We were actually talking before the talk started that GIS is, there's academic researchers like myself that use GIS and remotely sensed data, but there's actually a huge private sector of companies that are remote sensing and GIS, Teradata, you name it, there's a lot of them out there. And yes, I would say there are definitely efforts by private industry to use these technologies, not just for things like health, because actually, in the big scheme of things, there's not as much money in global health as there are in other fields, but for transportation projects and things like that, I do believe that there's a lot more public, investments in this technology to get the leg up, for sure. So that's a really good question, and actually you wouldn't think it, but it's an open debate in health sciences. We do believe that eating raw shellfish, you can directly contract cholera from eating like oysters that are in an area where these copepods are, where cholera is. But by and large, it is not considered a foodborne disease. So it really isn't passed, and that's partially because you have to ingest so much cholera in order to actually get it, that what you would pick up off of food, you might be exposed to it, but you wouldn't actually come down with an acute case. You essentially have to drink an 8-ounce glass of cholera water to get cholera, which sounds really pleasant, doesn't it? Yeah. So cholera is a diarrheal disease. And so essentially what happens is the cholera gets into your intestinal stomach and then your intestinal system. And you shed water. Your body just sheds water to try to get rid of the bacteria itself. So it creates massive watery diarrhea, and essentially you die of dehydration. And so the major treatment, and it's part of the WHO's and Gavi and a few other major global health organizations, is called oral rehydration therapy. And it's water with some salt and sugar thrown in. It's basically rebalancing the electrolytes of your system. And when children get cholera, the first thing their parents know to do in Bangladesh is to give them oral rehydration solution. So they're force-fed this stuff. And actually, ORT is much more effective even than a saline, or like an intravenous saline. It just works better to rehydrate the system. Of course, you can take antibacterial. You can take a Keflex or one of these big Cipro. Actually, ciprofloxacin works really well to get rid of cholera. Because it is a bacteria, you can use antibiotics to get rid of it as well. But oral rehydration therapy is the first line of defense in the developing world. Yes. Absolutely. I think that there are many countries, especially in Africa and actually in Southeast Asia, where the situation, the sort of infrastructure, the public health system is getting worse rather than better. And there's a lot of reasons for that. Political conflict is a primary reason in Africa why we have these public health infrastructures that are failing. There's also seems to be less and less money going towards global health. USAID in the United States used to give a lot of money to countries to help them develop their public health infrastructure. That money is increasingly going away and probably will go further away in the next 4 years. And so we have these areas that are really, really vulnerable. Cholera, you can't get rid of it. It lives in the environment, right? It's naturally part of the aquatic biotic system. And so therefore to eradicate it completely is almost entirely impossible. Same with malaria. It's almost entirely, you can't get rid of mosquitoes, right? Like, I wish we could get rid of mosquitoes, but it's just not possible. And the same thing is true of cholera. So it will always be part of our environment, and it will take advantage of places where the public health infrastructure is failing. So I have no doubt that we'll see another pandemic, actually, in the future. Yes. Yes. Types. So there are two major oral cholera vaccines on the market. They are both they have an efficacy of like 50 to 60%. By comparison, measles is 98%. So that tells you how effective they are. They're pretty good, actually. That's not too shabby. And they are only really effective for about 2 to 5 years. So it's like if anybody's ever had a yellow fever vaccine, you have to get it every 10 years in order to keep it current. The same is true with cholera, but it has an even shorter time period. They are targeted to all 3 biotypes now, so they are effective against all 3 of them. And they're really only used when an epidemic occurs. So we don't give it prophylactically, where I say, oh, I'm going to Bangladesh, and my doctor says, oh, well, we better give you the cholera vaccine. Instead, what happens is an outbreak occurs, and the WHO and UNICEF and a few other organizations have stockpiled this cholera vaccine, and they dump it into the system in, say, Bangladesh when an epidemic occurs, and vaccinate as many people as they can. And that's really the tactic. And the reason for that is that only 2 to 5 year effectiveness. With vaccines that are that, sort of short-lived, it doesn't make sense to try to keep it up in many of these countries over time. It's too expensive. Yeah. It is. Yes. Yes. Mm-hmm. Mm-hmm. Yes. Absolutely. We actually call this cultural ecology in my field. There's this entire area of study where cultural practices have sprung up as protection against certain ecological conditions. And this is one of these examples. It is ubiquitous in Southeast Asia to drink tea, right? When I go to Bangladesh, we stop at a little roadside guy. He's got a thing of tea boiling. He pours boiling water over my cup and then pours me a tea and gives it to me. And I am usually comfortable drinking that because I've watched him boil it, and I know that he's killed whatever microorganisms are going to be in that water. And I actually subscribe completely to this idea that there are cultural practices that spring up that are related to, people don't even know it, right, but are related to helping them stay healthy or whatever the case may be. Yes. Yeah. Yeah, I know exactly. Like, sort of this weird timing on that particular one. Yeah, in the back. Mm-hmm. So, predicting bacterial and viral evolution is another area that's sort of at the forefront of cutting-edge science. I've actually done quite a bit of research trying to do exactly what you're saying. We're not particularly good at it yet. But if we can understand what factors in the environment are forcing evolution to occur, so I work mostly with influenza in this particular regard. What is it about the human habitat that creates recombination and then forces viral evolution of a new, flu type? What are the interactions that need to occur? If I can have information on birds and households and domestic birds and wild birds and how they interact and whatever, then we can sort of predict the hotspots for where viral evolution might occur or where bacterial evolution might occur. But this is really in its infancy. And it's partially because you need really micro-scale data to be able to do this. And you need viral typing data. So I need to know what the genome of a virus or bacteria looks like to understand how it's evolving over time. And that's very expensive. There's not a lot of people who are willing to invest in a large-scale application of that. But it's a very, very exciting area. We call it landscape epidemiology, or landscape genetics. And so you're kind of you're at the forefront with your question. Yes. Yeah, so this is one of the theories, and it's the dominant theory in the field right now. In the 90s, when cholera made it to Peru, and we had this massive Peruvian epidemic, the question was, well, how did it get there? We're pretty convinced that it has something to do with the shipping lanes that go across the world. These huge, massive ships, right, they take on water in the harbor that they're in, and then they sail across to, and then they dump their, what's called, they dump their bilges, right, and they have ballast water. And we're fairly convinced that that's how the Peruvian epidemic started, that it was some ship from Southeast Asia that delivered a payload, into a perfectly pristine aquatic microsystem that cholera just took off in because the copepods were there. So that would be fantastic, wouldn't it? It's actually really challenging because shipping isn't just, it's not just the United States shipping around the world. There's organizations and companies from different countries and whatever across the globe that are responsible for shipping. And they all have their own standard operating procedures. And they all have their own way of doing things. And they're all trying to save money and make a profit. And so to enforce something like that is really challenging. I do know I'm from Seattle, Washington, and we have a huge shipping area right off of Seattle in Elliott Bay. And ships are actually asked to dump their ballast water out in Puget Sound prior to coming into Elliott Bay, and they're not technically allowed into the bay if they don't. So different areas are trying to protect themselves in different ways. But it is a major concern. I mean, that's how we think dengue fever made it to the Americas. Tires that were being shipped from Southeast Asia had a little bit of water in the bottom of them. You know how that happens on your tire swing? Mosquitoes, they love that habitat. That's like the best place ever for them to hang out. And that's how dengue probably made it to the Americas, although we're not positive on that one. Yeah, I don't know. I'm not saying, yeah.
Well, I was just curious, since we're talking about evolution, in your longitudinal picture in your little area of Matlab, it looked as though you had the classic stuff back in the past.
Yeah.
And then after the new guy, the 0139 plate,
yep.
disappeared, the classic was replaced by the L-Tor.
And
so it looked like basically the function of the 0139 is to
wipe out classical. Actually, that is exactly what we're seeing. It's very interesting. There doesn't seem to be room for 3 different biotypes of the disease at any one given time. For some reason, in the sort of ecological niche that these inhabit, there's room for 2. And so, yes, what you'll see here is classical this is the old one. We call it Asiatic cholera. This is what struck London in 1800s, right? And L-Tor was sort of newer on the scene, but it wasn't so bad that it actually wiped out classical. And that's because they don't offer cross protection, right? So you can have both of them, and people can get sick with both of them. And then, yeah, you have 0139 come on the scene, and all of a sudden, classical disappears. It wiped out classical. This is sort of a classic example of interspecies competition. And it even happens at the sort of this micro bio scale, and you can watch it with bacteria and viruses around the world. It's quite fascinating. Yes. Yes. Yes, it's a good question. Yeah, related to typhoid too and other sort of waterborne diseases. Yeah. So typhoid's a little bit different because it doesn't have this commensal relationship in the environment with the copepods. And if you remember really early in this talk, I said there's only a few diseases that we're super concerned about climatic conditions with. And most of them are ones that have some sort of tie to the environment above and beyond humans. Typhoid is mostly harbored in humans, transmitted through water by humans, but there's nothing kind of in between. Cholera is interesting because it has that copepod thing, right? So it actually exists in the environment by itself, commensally with these copepods. And it's really the copepods that are affected by climactic conditions, right? Same thing with malaria. Malaria it doesn't only exist in the human population. It has that mosquito component. And the mosquitoes are what are affected by the climate. Precipitation, temperature, all of that affects mosquito habitat. So that's what, there's a really small subset of these diseases, and they're bad ones. Don't get me wrong, malaria kills millions of people a year that are so sensitive to climate, and that's one of the things that makes cholera kind of unique.
Okay, I think perhaps we should cut the formal questions and continue the discussion upstairs.
Great.
And thank you once again.
You're welcome. Thank you, everybody.